All right, the last thing I want to talk about, going back over everything from Module 7, elimination, substitution, all that good stuff, is this whole idea of sometimes we don't get our normal answer. Sometimes we get this, no solution, or we get the other phrase, which is something we had not heard before until this year. And all it is two lines that never touch for no solution, and then two lines that end up right on top of each other. So basically the same line twice. That's when infinitely many happens. But as far as mathematically, what that looks like, it really comes down to true math versus untrue or false math. So let's look at this first equation or system, because a system is two different equations put together. And this will kind of help reinforce the last lesson also. What method should we use? Most people here would use elimination. There's nothing that will eliminate right off the bat. But if you multiply by -3, you can get some elimination to happen, because you'll have -3x plus 9y equals 15. And I'm going to scribble through this one so we don't get distracted. So for adding, we would add because we want elimination. 3x and -3x go away. -9y and 9y go away. And I have one mistake here. -3 was being multiplied by 5. This should have been a -15. And that's important because that -15 is going to also go away. So when everything goes away, I like to have my students write this. We have nothing equals nothing, or 0 equals 0. Okay? So just to review, if I distributed by -3, I'd get -3x, positive 9y, -15. That's the opposites all the way. That's straight cancellation. And when this happens, because that's a true statement, that means we have infinitely many solutions. Because what you can't see, because it's kind of disguised, is these first two lines are really the same line. And the only way to really see it is if you were to put both in slope-intercept form. You don't have to do this, but just kind of an extra teaching point here. We have 3x minus 9y equals 15. If you were trying to put it in slope-intercept form, you'd subtract 3x. You'd have -9y equals -3x plus 15. You would divide by -9. And you would get y equals 1/3 x, and you would probably have to just leave that. Doesn't come out real good. 15 over 9 does reduce to 5 over 3. That's the first line in slope-intercept form. The second line, which was x minus 3y equals 5, you would subtract x. You'd have -3y equals -x plus 5. You would divide by -3 all the way across. And it wouldn't take you very long to figure out you got the exact same line. So we don't see that when we're trying to do these problems, but it comes out right here. Our variables fall away. We're left with a true statement. That's why it's the same line, and that's why we have infinitely many solutions. So number one, infinitely many. number 2. Now this is a problem I'd probably do substitution on. We've talked about it several times now. They're both equal to y, so they have to equal each other. But once you start trying to move stuff around, you would notice something's going to happen. Your variables go away, and you're left with these two numbers. Now, if you wanted to, you could keep going and keep moving. But eventually, you're going to have to stop and say, this is a false statement. Therefore, this problem has no solution. And honestly, this is not hard to illustrate at all. Both of these lines are already in slope-intercept form. One of them goes through 0, 5, and then you go up 4 over 1. And I'm just doing the eyeball method here. But then one of them starts at negative 3, and you go up 4 over 1. They're parallel. They never cross. That's why it's no solution. Variables go away, false math left over, no solution. So we use elimination on the first one to prove infinitely many. We use substitution on the second one to prove a no solution. When you see this problem, think about which method you might use. Now this one is kind of weird looking, but I'm actually allowed to turn that second equation all the way around. It's called the symmetric property. Which means now, if I get that first one out of my way, we actually are lined up. We actually are in a good spot to do elimination. Let's multiply by 2 up here all the way through, and we'll get 2x minus 2y equals negative 16. Now we can add those equations together, and x's are gone, y's are gone, nothing left. But over here we didn't get that cancellation. We got negative 23. So the variables went away. Our math yields a false statement. That means this system must be another one of those parallel lines. And so this one, after we moved it around, it wasn't that bad at all. At first it looked a little weird, but we flipped the left and right side, and everything lined up, and we were able to finish it out. No solution. We'll use elimination twice. Last problem. Here's the first equation. Here's the second equation. Now, when I say a problem like this, I would probably actually use substitution, but I would do this step. I would add 30 to both sides. So the first equation becomes 5x plus 30 equals y. And now I have y all by itself, and I'm ready to go do a y for y substitution. But when I do that, I'm going to have 5, because remember now I'm using the other equation. I'm putting 5x plus 30, putting all of that in for y. Now I'm going to follow the rest of the pattern of the second equation. I'm going to distribute, and this is one where you should sort of recognize what's about to happen. I get the same thing on both sides, and when I start trying to move things, everything starts canceling out. So whether you stopped when it said 150 equals 150 or 0 equals 0, you figured out that you've got a true statement. We're back to infinitely many solutions. Alright, so we use substitution twice, we use elimination twice, we got infinitely many twice, we got no solutions twice. Just want to make sure you understand when that happens, it's all about the variables going away and whether your statement remaining is true or false.